Okay, welcome back. I noticed on my videos yesterday I said, all right, every time I started a new video. So I was like, I'm not doing that on this video. But all right, here we go. Let's go with 2.3. So let's do another problem like the ones we were just doing. So let's take y equals x squared times x squared minus 25 times 3x plus 1, and we're going to graph it. Okay, so if you like the, sort of plain connect the dots version, that's fine. I'm going to do this via the sign chart, just because I think that there's actually more to be gained by the sign chart. Okay, so the first thing that we're going to want to do, we want to make sure that our polynomial is completely factored. And this is not completely factored. This x squared minus 25, we can factor that further. Excuse me. Okay, so we're going to factor completely. So it's going to be x squared, x plus 5, x minus 5, 3x plus 1. Okay, next, what are the roots? Okay, our roots are at x equals 0. That's from this x squared. So that has a multiplicity of 2. Let me move this a little bit. Okay. X equals negative 5. That's multiplicity 1. X equals 5. Again, multiplicity 1. What about this 3x plus 1? What's the 0 there? That's right, negative 1/3. Okay, also with multiplicity 1. We have to remember, solve that to get 3x plus 1 equals 0. So now let's make the sign chart. We're going to make sure we put these numbers in order. So that means starting from negative 5, then negative 1/3, then 0, then 5. Okay. To the left, we're going to put the different factors. I don't care about the order, not here. Okay, little dashed lines underneath my zeros, or underneath my roots. X squared has its root at 0. Remember, I put a little filled in circle there. X plus 5 has a root at negative 5. X minus 5 has a root at 5. And 3x plus 1 has a root at negative 1/3. Okay. Now, x squared. X squared is a quadratic, it's a parabola, so it's always going to be positive here, right? Now, it could be always negative if there was a negative in front, but there is not one here, okay? And usually I don't even deal with that. What I would do is if I had a negative in front, I would just add a negative to my sign chart and just put it all negative. But this is all positive. Set that 0 where it's 0, okay? X plus 5. X plus 5, this is a line sloping up, crossing at x equals 5. So it changes from negative to positive there. This is a familiar sort of idea. X minus 5 changes from negative to positive at 5. 3x plus 1. The slope here is 3. So that means it's going to change again from negative to positive at its root. Okay. 3 negatives gives you negative. positive, negative, negative, positive. Okay, now we're just going to sort of, as a sanity check, let's take a look at our end behavior. What's our end behavior here? Our end behavior is x squared cubed to the fourth, x squared cubed to the fourth, 3x to the fifth, right? You could also just add these up, 1, 2, 3, 4, 5, and then make sure you get the sign right. 3x to the fifth, that was one of those odd ones, so that's what the end behavior looks like. It should start out negative and end positive. Look, our graph's going to do that. Okay? Let's go ahead and graph this thing based just off the sign chart. Okay, so at -5, -1/3, 0, and 5. Okay, so all right, starts out negative. Between -5 and -1/3, it's going to be positive. Between -1/3 and 0, it's going to be negative. But now look, between 0 and 5, it's going to be negative again. And then it's going to be positive after 5. Okay? And that's what you would get if you did it by playing the connect the dots game, the other method. Okay? All right. Let's take a look at reversing the process. What do I mean by reversing the process? Well, some problems you're going to get are going to look like this. So they're going to actually give you the graph first. So let's say we have we do that again. The beginning of the semester, I would have just started the videos over again, but I'm no longer doing that unless there's really a reason to. Okay, so let's say we had a graph that looked like so. And the question is, find a polynomial of minimal degree that matches. Okay, and you should probably, and also they take leading term equal to 1. I'm sorry, leading coefficients is plus or minus 1. Okay, so we're not going to mess around with having like, well, there's other ones that could do it, but we're not going to mess around with that. Okay, so find a polynomial, minimal degree, and leading coefficient plus or minus 1 that matches. So, as you can see, you're going to have a bounce at, what is that, -5, and a cross at 2. Okay? Okay, so we're going to just have y equals x plus 5 squared times x minus 2. Okay, now that's fine. What if I would have given you this graph, though? Okay, so that one's in orange. I'm sorry if you're blue-orange colorblind. I'm red-green colorblind, so I feel your pain, but I think these are different enough. So what's that? That's got the same stuff, but now it looks sort of reversed, right? So that one's going to be y equals, that one's going to have a negative on there. Okay, so I hope you can see the difference. Let me move these. Get this out of the way. Nope. Put a boundary between these problems. Okay. All right, I'm actually going to continue on. I'm going to make a new page here. So we only got one more problem left. So we're going to do another one. Similar idea. Okay. So let's say I had a graph. This one's going to have just all the different crosses. They're going to all be crosses here. So a cross at 3, -3, a cross at 3, and a cross at 5. Okay. But now, one thing that you should notice is that the end behavior starts up here and down there. So that means it's a negative even graph, right? It's a negative even graph. So y equals negative x plus 3, x minus 3, x minus 5. Okay. Similarly, just like in the other one, if I would have given you this, that one's going to be the positive. Okay. Now, just one last sort of thing that is sort of in the problem set. Just want to mention it. So, a polynomial with n of nth degree has at most n minus 1 turning points. Okay, so if you look, for example, these are third degree polynomials, and they have 1, 2 turning points, or 1, 2 turning points. Let's look at some of the other ones. This one was a third degree polynomial, 1, 2 turning points. This one was a fifth degree polynomial, 1, 2, 3, 4 turning points. Okay. What was this? A fifth degree polynomial, 1, 2, 3, 4 turning points. Okay. Now, you may not have exactly n minus 1 turning points. There are examples where you would have less. For example, y equals x to the fourth. Y equals x to the fourth just looks like that. Okay. So that only has 1 turning point. All right. But this is at most. All right. That's it for section 2.3. I'll see you guys on 2.4. I'm getting close to the class time. Look forward to seeing you guys next week.